Hey, good afternoon. I'm going to model a very interesting molecule today. And so what I'm going to model, I'm actually going to model a molecule called Buckminsterfullerene. That's also C60. And this is actually a very interesting molecule. It actually won the 1996 Nobel Prize in Chemistry. Three scientists were actually recognized for this work. Harold Kroto, Robert Curl, and Richard Smalley received the Nobel Prize for this. It was actually the Buckminsterfullerenes were first theorized around the late 60s and 70s, and then they were discovered in 1985. It's actually a black solid that forms when it's dissolved in various hydrocarbon substances. It'll actually form kind of a purple solution. And it's also very interesting. It's very hydrophobic, of course, because there's only carbons. There's no hydrogens, so therefore no hydrogen bond donors. Are there hydrogen bond acceptors? Well, they're all sp2 hybridized carbons. And if we consider some research by Max Peretz in the 1980s, there's actually a paper on this that suggests that benzene will serve as a hydrogen bond acceptor due to its the double bonds will actually accept hydrogen bonds, and so we see this in proteins all the time. So that could be very interesting chemistry. But it is a very hydrophobic substance, and of course they were looking at Bucky Balls for reasons of maybe seeing if we could use this as a drug delivery mechanism or other applications. And so Bucky Balls, we would consider this one of the three major allotropes of carbon. The first being, of course, the diamond with a very hexagonal, very rigid structure. And that's the the hardest substance known to humans. And of course, then graphite, of course, is kind of the opposite of that. It's a very loose structure, and it's very powdery. And so then Bucky Balls are kind of in between there as well, too. So it kind of forms a circle. There's 20 hexagons and there's 20 pentagons. So it kind of looks like a football. And by a football, I mean the international definition of a football, which we in America would call a soccer ball, right? So if you've ever seen a soccer ball with those pentagons. And it presents a really interesting challenge if we're going to model these if we're gonna try and do some molecular modeling of Bucky Balls. It would present a very interesting challenge because you have to get the geometry right, and you have to get the pentagons and the hexagons positioned right. Now, if you look at a soccer ball, let's look at how we would model this. If you look at that soccer ball, none of the pentagons are in contact with each other. There's always hexagons in between every single pentagon. And that's actually very important when you're modeling this. So when I model this, when I start out, I'm going to start out by modeling, you would think, okay, let's just start with the hexagons and then kind of put everything around it. No, you want to start off with a pentagon. So if I'm in MOE here, I'm going to start off with, and of course I need the sp2 hybridized 5-membered pentagon. I'm just going to call this a Bucky ball right here. And so one thing I know, here's my pentagon, and I know if I just click here, I need a hexagon here. And I'm going to put a hexagon here. And let's just see if I can put a hexagon right here. And I don't think I can do this, but no, it's not going to let me do that. So what I need to do is just do 2 carbons, and then let's connect this with another bond right here, right? And then I need to do the same thing here. Let's put 2 more carbons, and then I'm going to put another bond. And so now I've got, it doesn't really look very pretty yet because, obviously the hexagons aren't perfect, but I've got my pentagon right in the middle, and I've got all my hexagons right around it, right? So now what I'm going to do now, if I just take from my pentagon, each spoke, each of the 5 spokes on the pentagon goes to a bond and then another pentagon, right? So what I can do here is take these 3 carbons and put another 5-membered ring here. I'm going to take these 3 carbons and put a pentagon here. We're going to take these 3 carbons, another pentagon, and then we're going to take these 3. Right? Okay. And so now I've got the pentagons. I should have, oh, I forgot one right up here. So we need one more pentagon right up there. Now I should have 6 pentagons around the ring, and I've got a central pentagon right in the middle, right? And if we just kind of look at this arrangement, I've got 46 atoms. However, well, for one, we do need to consider a couple little things. That there's some of the double bonding arrangements are going to get kind of interesting. So let's just fix that. Whoops. I want to do that. Okay. So we're going to change that around. And move that. And because of the way MOE does this, sometimes you have to finagle the bonds just a little bit to get it to work just right. I think what I'm going to do is change that and that guy. And let's see. There, and I think that should be good enough for now. Right? Now let's put my force field on. I'm just using the amber EHT force field, which is default in MOE, and then I'm going to do some energy minimization. Very simple molecular mechanics, just to get the geometry right. You also see that we do have a slight concave appearance, right? Which is actually kind of unusual because in organic chemistry we've learned that sp2 hybridized carbons are trigonal planar geometries, so it should be flat, it should be planar, but in a Bucky ball, of course, it's not flat. Of course, it's actually a sphere, and because it has to be in order to form that sphere. And while we do like things to be planar, in a Bucky ball, of course, it due to the constraints, we do have to have a slight angle for that, and that is allowed. So it doesn't, sp2 hybridized bonds don't have to be perfectly planar. There can be a slight angle to that. But we really can't make a really small angle because then there will be too much ring strain involved in that. Okay, so now, if I just kind of look at this, you'll see I've got 42 atoms, and the other thing, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it looks like I've got 12 hydrogens. And if I take that, that means I've got 30 carbons, because 42 minus 12 is 30. So what I'm going to do now is I'm going to just copy this, and in my clipboard, I just want to copy. now I've got two Bucky Balls. I'm going to take the second one, and in MOE, I'm going to hit Shift Alt and the middle mouse button, and that should allow me to move some atoms like so, right? So now I've got both halves of the soccer ball. Now, obviously, the soccer ball would need to form a sphere, and I haven't formed the sphere yet, right? But I've got the basic frame in place, and now I've got 84 atoms minus those 24 hydrogens, so that means I've got 60 atoms. So I've got the right number of carbons now. And what we also want to remember is that each pentagon, like this pentagon right here, is only connected to a hexagon, right? If I want to connect it to the next, if I want to connect it to another pentagon, I can only have one connection. So like this carbon, for example, should go here, and I'm going to connect that. Or actually, I think what I want to do is connect this one to this, right? And so then this needs to connect to the next pentagon down here. So I've got a pentagon here, and I've got a pentagon here. So now I'm going to connect that. And then we're going to just go around. This is the easy way of building a Bucky ball, right? We just keep going around in a ring. And we're connecting all of our pentagons. Now, it looks kind of interesting because when you see it, you don't really see it initially because you're like, wow, this is kind of an exercise in 3D visualization because you're like, wow, I'm not sure what's going on here. But trust me, when we get done with it, we should have a perfect Bucky ball. Go right around, and it does kind of look cool this way. I need to connect that, and then we're gonna, I think this is the last one. There we go. We'll connect this around. Okay. All right. So there are some interesting things here. I think probably need to it's not quite a perfect Bucky ball yet, so I need to connect. But let's get my minimization first, and then hopefully I can resolve some of those other things. So here's my ball. We're almost there, right? Now let's disconnect him. We just need to resolve a few of these little things here. Let's do one more energy minimization, and there we have it. There is our perfect Bucky ball, right? Just just to verify, I've got 60 atoms in the ring. I can of course visualize this with ball and stick structure, and you can see there's space inside. It looks like a perfect geodesic dome. And then what we can, if we visualize this with a space filling representation, we can get, this is what it would look like with the van der Waals surface. So it looks like a really interesting molecule, and it's also, this is a really good exercise for you if you're learning molecular modeling. You want to present yourself with a really good challenge to build a perfect Bucky ball. So I hope you enjoyed this video, and let me know what you think about the molecule. If you have any questions, leave those in the comments below. If you think maybe Bucky's should sell a Bucky ball, if you've ever been to the famous fueling station, I'm certainly a fan of Bucky's as well, but this does not mean that I endorse, or this video is certainly not endorsed by Bucky's at all. I just like the store. It's pretty cool. So leave a note in the comments below. If you have any questions, go ahead and hit the like button and subscribe to the channel. Hit the little bell icon. That always helps me out. So again, thanks for watching, and I will see you in the next video. Thank you.